Thank you for joining us at ArtScience Museum today for Complex Systems. In today's program of talks, we look at complexity as a new interdisciplinary approach to science and society, bridging traditional academic frameworks and paradigms with real-world systems. This program is organized in collaboration with NTU as a satellite event of the Conference on Complex Systems 2019. This is the biggest and most important annual meeting of the international complex systems community, and it's being held in Asia for the first time in Singapore at NTU. It's an incredible privilege for us to be hosting two visiting speakers of the conference this afternoon. We have Sara Walker. She's assistant professor at the School of Earth and Space Exploration at Arizona State University. And she'll be speaking on the topic of Matter Like Us, Searching for Complexity in the Universe. And Rika Preiser, who is senior researcher at Center for Complex Systems in Transition School of Public Leadership at Stellenbosch University. She'll be sharing about art science collaborations for reimagining more sustainable social-ecological futures. Sara Walker is an astrobiologist and theoretical physicist. She's interested in the origin of life and how to find life on other worlds. While there are many things to be solved, she's most interested in whether or not there are laws of life that could universally describe life here on Earth and on other planets. In the talk, Sara will discuss the new insights complex system science is providing into the nature of life and how they can inform our search for life beyond Earth. And we will be very happy to open the floor to questions right after her talk. Please join us in welcoming Sara Walker as our first speaker of the day.
Thank you so much. So I'm really honored to be here, and this is my first time in Singapore, and I've been having a fabulous time so far, so it's all really great. As was introduced, I'm actually an astrobiologist and theoretical physicist, so I think at the intersection of physics and astrobiology, which means I'm really interested in what universal properties life has. And so I was actually trained in cosmology when I went to school, and when I'm thinking about looking for life, I'm thinking about it from a slightly different perspective than people do traditionally, which is a lot of people on Earth will think about life as being cellular, and will think about, organisms like us. But when we think about looking for life astrobiologically, we have to really think about what the magnitude of the problem is. And so oftentimes you'll see images like this in cosmology where we figured out what a significant fraction of the universe is composed of, right? And so people will talk about the fact that isn't it remarkable that only 4% of the universe is baryonic matter like us, and we've figured out all of this remarkable physics, but there's still a really huge fundamental missing component, which is we have no idea how much of the universe is like us. And what I mean like us is alive, right? We don't know of any other planets that have life on them, and we don't know of any other worlds that have intelligence. And so this is actually really a problem in complexity science, as I'll try to articulate in the talk today, in terms of trying to understand how much of the universe actually becomes complex in a way that we would recognize as being living. So this is sort of my motivating framework for thinking about things. The question I've kind of become obsessed with in my career is actually answering the question, what is life? And so I think this question is a lot harder than most people really give it credit for. We think about life as being sort of obvious, but it's really not obvious what life is if you think about it just a little bit more deeply than just thinking about self-reproduction and cellularity. It actually ends up becoming an incredibly hard question. And so there's been a long tradition of people in my field in physics thinking about what is life. One of the most famous works on it was actually done in 1944 by a very famous physicist named Erwin Schrödinger, who's most famous for his work in the foundations of quantum mechanics. But he actually gave a series of lectures in 1944, well actually in 43, the book was published in 44, in Dublin at their Institute for Advanced Study on the topic of life. And that book was actually credited with inspiring Watson and Crick to discover DNA. Schrödinger basically had some really elegant arguments about what he thought was necessary for the physics of life in that book. And I encourage everybody to read it. But the thing that really sort of challenged me about that book was at the end of the book, he appeals to this idea that other laws of physics might be necessary, because he goes through this sort of long set of arguments about what physics can explain, and then there's so many things that we really can't explain about life yet with our current formalisms, that he actually suggests a pretty radical idea that we might even need new laws of physics. And actually, this is one of the things that I work on in my career, is trying to understand what those new laws might be. And so what I'm going to do in the first part of this talk is still continue a little bit on the philosophy of what I think those things are, and then I'll get more into sort of the concrete work that we do trying to understand it. So when we're thinking about what we actually understand about the universe, physicists are quite proud of this kind of structure that has evolved over the last couple centuries. So in the 1800s, we unified electricity and magnetism, and then we realized there was a weak force, and that was unified. And so we have this idea that we're going to have a theory of everything, which is going to describe all of physical reality. So all of reality will be described by these very simple, elegant equations that physicists have come up with. But as my colleague David Krakauer at Santa Fe Institute says, a theory of everything is a theory of everything except those things that theorize. I always laugh when I read this quote. I absolutely love it. I think it's very telling about what it is that we're talking about. So we have a really deep understanding of the world. Like if you think about that plot I had on the first slide, you know, we understand a lot of the universe, but we still don't understand ourselves, and we don't understand our ability to actually understand the universe. And I think this is a really important clue to what life is doing. So when I think about what life is, I actually try to think about the things that life does that no other physics that we know about can do, right? And one of those things is actually build theories about the world. And so to try to get at the physics of life and understand what life really is, I like to think about examples like this example, which is the process of anti-accretion. If anybody in here has ever studied planetary formation, you may have heard of accretionary processes, the fact that planets accumulate by rocks clumping together and then forming larger bodies. We're the only planet in the universe that we know of that anti-accretes. And what we do is actually launch metal boxes into space, right? So we call them satellites. We do this on a daily basis. And if we really think about what that is as a physical process and what's involved in that, there's something really key to that process actually being able to happen on our planet, and that's technology and science. And what I mean by that is, in order for that physical process to happen, you have to have intelligent beings, some kind of system that understands gravitation, that has a kind of thing that we call the laws of gravitation, knowledge about the physical world, and the technology to actually implement that knowledge. And so in order for this process to happen, it actually requires physical systems to have some kind of information. They actually have to understand about gravity. This would not happen on a planet unless there had been an evolutionary history that acquired such knowledge. And I think this is a really important clue to what life is. Another example where I find this really interesting and where I start to talk about what I call sort of physics of information, although people mean different things when they talk about information, so I use these examples to try to clarify, is when we talk about the physical processes in the universe that can make elements, we again encounter a case where there's a unique role for technology or intelligence, in the sense that we can look at the elements in the periodic table and we can articulate all the physical processes in the universe that make the elements. So some of the elements were made at the Big Bang, some of them were made by the explosion of supermassive stars, some of them are made by the death of supermassive stars, some of them are made in neutron star mergers and massive explosions that happen in our universe. But if you get to the very heaviest elements in the universe, they are only made with any kind of reliability and any kind of length to their life, which is still very short, in the laboratories on Earth as far as we know. And that's because you have to have a really precise control over nuclear physics in order to be able to create those things. So there is this kind of idea that intelligence is actually a physical process in some sense, and that you actually have to have a physical system that has some kind of knowledge to make this process happen. So just as with anti-accretion, again, we see an example where there's something that happens in our universe that wouldn't happen without information or without knowledge. And so I kind of alluded to this idea that I'm really interested in looking for whether there's universal principles of life and whether there would be clues of life. And so we know about the laws of gravitation. We really respect those as being universal. But one question we might ask are there universal laws of biology or universal laws of life? And I think if there are, they have something to do with information, because of the examples that I was giving before. Because if you think about the things that biology does quite uniquely and that living things do that no other physical processes can do, it's process information and use information to actually do things in the world that would be impossible otherwise. And so one of the arguments I've made throughout my career is that the origin of life itself is somehow the emergence of information in the universe, or the idea that information actually becomes an important physical cause in the universe. And so, so this is sort of my philosophy about thinking about what life is. And the question is, how do we actually make that kind of abstract thinking about life something useful that we can actually start to do real science with? And so the question, what is life, has been a philosophical question for thousands of years. It is not an easy question. And I think coming at it from this perspective is quite promising because it allows us to think more quantitatively about it and more constructively about what is the missing physics that's going to make us understand life and the physics in the universe that actually makes life possible. So the next question I'm going to ask, besides what is life, is whether planets are alive. And so this is going to seem like sort of an odd question, but it'll start to become a little bit clearer what I'm getting at in a couple minutes about why I'm thinking about it at this scale. So I'm an astrobiologist, and when we're doing astrobiology, we're actually trying to go out in the universe and look for life. And in some cases, it will be very obvious, like this one, that there's an example of a living world and an example of a non-living world. So Jupiter, we think, is not alive. Earth, we're pretty sure, has life on it. If you look at the surfaces of these two planets, they both have what we call in physics non-equilibrium structures on their surface. In the case of Jupiter, it's the Great Red Spot. In the case of Earth, it's our cities. And this gets to my argument about the fact that we actually really need a new kind of physics to really explain life, because physics is really good at explaining things far from equilibrium. They're structures that can self-organize and maintain structure, like the Great Red Spot. It is not so good at describing why cities have organized on the surface of our planet and why they cover the planet. I think that requires an evolutionary history, and that requires, in some sense, information in the same sense I was talking about before. You can't build a city without information about how to build a city. You have to acquire that information over time, and it requires a globally organized civilization in order to be able to do that. Now, this is an obvious example, and the challenge for astrobiologists is that we are not necessarily going to know life when we see it. We recognize cities, right? Cities are pretty obvious to us that those are built by living systems. And whether or not you agree with me that a city itself is alive is another thing, but you at least recognize that life is necessary to produce a city. What about planets around other stars? Is it going to be so obvious what life is on their surfaces? It's probably not, so we have all of these so-called exoplanets, which have been discovered around other stars, and we know of thousands of them now, so this is just an artist's rendition of one. We get a tiny little fraction, little bit of light from each of these exoplanets, and we have to infer whether life is existing on those planets. So if you're thinking already about that, life was necessarily going to have to already be a global process. It's going to have to be occurring at the scale of a planet, and actually influencing the planetary atmosphere in the same sense that our Earth has been influenced by life in order for us to be able to detect it. So when we're talking about exoplanets, we have to have planetary scale life for it to be detectable. And what I mean by that is, for example, one of the greatest biosignatures people talk about, signs of life on other worlds for exoplanets, is oxygen. Oxygen in our atmosphere is a byproduct of life, right? Life had to evolve photosynthesis, and then it had to interact with our planet because most of the oxygen being produced early on by photosynthesis was actually absorbed by iron, but then the iron became saturated, and then the oxygen built up in our atmosphere, and we became detectable as a biosphere. So life is detectable as a planetary scale process. But how do we understand what life is as a planetary scale process? And this is when I'm going to go back to this idea that life does things with information that other physics couldn't. So people in here probably just had lunch recently or ate something. Hopefully you ate today. This is what's happening inside your cells right now. This is a metabolic map. It's basically a map of the kind of chemical transformations that happen inside a living system. They're tightly controlled chemical processes. And what we can do with trying to understand these is to think about the fact that biology ultimately emerged from chemistry. And there should be some patterns in that chemistry related to how biology actually exists as an emergent property of chemistry. And so these kinds of reactions are happening inside your cells, but you're actually a living thing that's emerged from those patterns. And so one way I think about it is to think about the actual molecules themselves But then what we do, and this is where the complex system science starts coming in, is start to think about those molecules as patterns of like when they react with each other in terms of patterns of interacting molecules, we can actually represent them graphically in what's called a network. And so people in here are probably parts of social networks that might be a little bit more familiar, but if you are a person and you have a friend, you know, on Twitter or on Facebook or something, you can actually be connected to them by what's called an edge in a network, and then you could actually build up, you know, a friendship network in the same way. So what we do with molecules is we say if two molecules react together inside a living organism, that we can actually connect them, and then we build up this sort of connection of what molecules are interacting with what. And so in some sense, just connecting back to the first part of my talk, this captures the set of transformations that are happening in chemistry because it's a living chemistry. All right, so the hypothesis is that if you looked at a non-living chemistry, so we have our living chemistry now in a box and we want to compare it to a non-living chemistry, they should have different patterns. Because in one case you have physics of life operating, organizing that system, leading to emergent properties that we call living things, and in the other one you don't. And what we want to do with this is actually compare it at the planetary scale. So it's not just that I have some chemistry that's actually organized into me, but you also all are, you know, organized patterns in chemistry, and so are ecosystems, and so is planetary scale biochemistry. So we can actually take all of the chemistry that biology is doing on a planet and compare it to all of the chemistry that another planet is doing that's not alive, say for example Mars. And that's sort of one of the places we'd like to go with this. But what we want to understand first is how to represent Earth and its biochemistry from this perspective. So thinking about life as a planetary scale pattern in the organization of chemistry. So my group's been doing a lot of work on this, trying to think about it. And basically what we've been doing is taking huge genomic and data sets and trying to look at regularities in the organization of individual organisms like you and me, but more specifically, mostly microbes. Ecosystems, if you take environmental samples from a hot spring and you just look at the community of organisms living there, and then you take all the reactions and all the chemistry that we know that are happening across the entire planet. And what we're looking for is whether there's universal patterns in that chemistry that might distinguish it from random chemistry. And the way we would do that is actually looking at network properties. So it might be something like, if I'm talking about a friendship network, it might be how many friends I have compared to how many friends you have, because that's how many connections you have in the network. In chemistry, we think about how many molecules does this molecule react with versus this molecule over here. And that might be called what's called the degree in a network. And we look at those kind of properties versus the size of that biochemical system in terms of how many compounds it has in its reactions. So I have a different number of molecules that I use in my biochemistry than, say, does an E. coli. And what we find is actually, when you look at biochemistry as a whole, there's actually a pretty regular scaling behavior. So there's some predictability about how many molecules a molecule will interact with on average across all of biology. And it's a different value than we would see in random chemistry. And so biology has selected out some specific patterns that lead to a chemistry being alive versus not. And we're actually trying to detail what those patterns are. But the way that I think about it is really to think about this idea, this abstract idea of information actually is organizing these systems and looking for the patterns of how it's done that. One other thing that we're looking at more recently, which I think is pretty exciting, is to think about chirality of molecules also. So before I was just talking about the patterns of the way the molecules are interacting, but biology actually picks out a lot of particular features of molecules. And one of them is that the molecules in your body, a lot of them, like amino acids that make up proteins or the sugars in DNA, can come in two varieties. They're called chiral, left or right hand. It's actually that the molecules are mirror images of each other. And so what we've been doing is actually labeling every molecule in planetary scale biochemistry by whether it has a chiral property or not. And what we're finding is that there's extreme statistical regularities across all of biochemistry. So biology is structured in a particular way, not just with how molecules interact, but the properties of molecules it's selected out and how they're actually interacting to lead to these emergent planetary scale regularities that we see. So that's sort of one concrete way that we can start thinking about networks as patterns of transformations, as a manifestation of how information is actually allowing a system to follow specific paths through chemistry, what we call life, actually can be studied universally across biology on Earth. And so the third part of my talk that I want to talk about is how we can actually use this to discover alien life. Because I've been talking quite abstractly. I've been talking about information, this idea that there's this kind of missing physics in the universe that describes us, and it has to do with something about transformations in physical systems that are only enabled if there's information in the system. It's very abstract, right? But we can study those patterns in real chemistry and see what those patterns look like and compare it to non-living chemistry to living chemistry and see if we can tell a difference. So what I want to do with this is actually eventually, one, discover the physics of life, two, be able to understand the origins of life, and three, use that to detect aliens, right? So we have to build an entirely new framework to do those three things, which is basically what I'm trying to do. So it's a tall order. But the discovering alien life, I think, is really important. And I'm going to go back to the challenge I talked about before, which is we're now talking about looking for things like us, whatever we are. You know, it's a matter like us in the title because I don't think we really know what we are, right? We want to find something that's like us, but we don't know what like us is. And so we want to do that on exoplanets. I spent a lot of time thinking about exoplanets and how hard that problem is. And one of the analogies they could do is it's like looking for, you know, your keys under a lamppost, but you're actually not even anywhere near the lamppost because you don't even know where to start looking. So we know of one inhabited planet in the entire universe. One planet with life, that's us. And when we're thinking about looking for life on other planets, we have to not use the biases that we have about what life is like on Earth, which is one of the reasons that I've constructed sort of the framework that I've been talking about so far. And there's a lot of challenges with that. One of the challenges is that a lot of the exoplanets that we've discovered so far don't look much like our planet. But a lot of the other challenges are just really practical, technical challenges associated with exoplanets, which are, we don't know necessarily what life produces in a given planetary environment. So I've been talking about this idea of planetary scale biochemistry. There is a lot of discussion in astrobiology about the fact that you can't separate planets and the life on the planets. Right, so we think about life as sort of being this thin veneer that exists on the surface of our planet, but it's actually tightly coupled to the geochemistry of our planet and the planetary cycles, right? So oxygen is one example that I gave earlier, but pretty much everything about the Earth system is defined by life. And so, so when we're talking about life on Earth, we have certain things that we call biosignatures, gases that are produced in our atmosphere that are detectable across interstellar distances. But the problem that's coming up in exoplanet science is that dead planets can probably fool us. So for example, oxygen can be produced readily on planets orbiting other stars if the stars have different UV radiation, so they have different properties to the lights of the stars. For example, a red dwarf star has high UV flux. UV is really good at producing oxygen in atmospheres that have water in the atmosphere because it basically splits the hydrogen from the oxygen in the water molecule and can produce an oxygen-rich atmosphere in the absence of life. And so we do have this huge body of literature now that's evolved over the last 10 years in exoplanet science, basically studying this idea of false positives, that a lot of the molecular signature gases that we thought were completely indicative of life, like oxygen, are not, because they can be mimicked by non-living things. We also have a huge problem of limited data, so it's not like we're going to be able to see the planetary surface and be able to look at you know, continents and oceans and, you know, the exact spectrum of a planet. We're going to get a really, like a tiny pixel. And then we don't actually understand the compositions of exoplanets either. So basically our problem is we are looking for unknown biology on planets that we don't know their exact properties across interstellar distances with tiny, you know, a couple photons per planet data. Right, so this is, and we're going to try to do this to detect life. Right, this is actually how we're going to find life. Because it's probably, you know, very unclear if we have any life in our solar system or not. There are a few candidates in the solar system, which I'm happy to talk about in questions. So one of the things that we're doing in my group is actually taking this sort of network science approach that we've been doing for understanding planetary scale biochemistry to now understand the organization of atmospheric chemistry on living and non-living worlds. So if you think about the fact that I already made the argument that if you look at biochemistry or chemistry as it's organized in biology at a planetary scale, there's distinctive patterns in terms of how those molecules interact. And we've already made the argument that life is a planetary process. It's driving planetary cycles. It should also be driving the structure of atmospheric reactions. All right, so oxygen being present in an atmosphere is just an example. Once oxygen is present, it reacts with a bunch of other molecules, and it leads to a whole structure for the atmosphere of that network as far as how the chemistry is being transformed among different reactions. And so there's been some preliminary work done actually by some complex system scientists about 10 years ago demonstrating that Earth's atmosphere actually looks very different from this network perspective than do the atmospheres of Mars or Venus. And so you can actually show at sort of a crude level that Earth has some patterns that are associated with life in terms of the structure of the networks in its atmosphere, the patterns in the chemistry, as compared to other atmospheres in our solar system. And so I actually have a grad student working on a related project now trying to look at what are called hot Jupiter atmospheres. So these are, hot Jupiters are large gaseous giant planets like Jupiter orbiting other stars, trying to understand if we can actually model observational properties on exoplanets using network theory, using this kind of approach. And the idea there is that we're going to be able to then take that to terrestrial-sized planets with observational constraints and be able to get at what I really ultimately want to get at, which is to think about planetary evolution as a whole as a set of interacting networks. Biosphere, biochemistry that I've showed you is one. The atmosphere is another, right? So you'll have all the patterns that biology is mediating in chemistry on the surface of our planet, all the patterns that's forcing in the atmosphere, and then the patterns in the geochemistry. And you can actually talk about the evolution of chemistry of living and non-living worlds from this perspective. And this starts getting really interesting when you think about technology as a planetary process and also a part of planetary evolution. So the noosphere is this kind of idea that knowledge is going to be this kind of fourth or fifth biosphere, or fifth geosphere in some sense. So geospheres are all the interlocking Earth systems that are interacting to make our planet what it is. Right? So you have the hydrosphere, which is the oceans, the geosphere, which is the planet itself as we usually think about it, the biosphere and the atmosphere. And then the noosphere would be like technology as another globally integrated system. The interesting thing is from this perspective, you can also think of that as a natural product of the planetary evolution because even the chemistry that we evolve technologically, all the chemistry that we've invented can be built into this as thinking about the planetary diversity of chemistry. So it's one example where I'm trying to think about this idea that information is really the essential thing of life, but it manifests at a planetary scale in terms of how these networks are interacting and evolving. So I'm going to have plenty of time for questions because I have one slide left, so it's good. So I'm just going to end on a quote. This is also one of my other favorite quotes, which is from Albert Einstein, who's been a great inspiration to me, about how one can best feel in dealing with living systems how primitive physics still is. So I think we actually really don't understand what life is. We don't understand what life does to a planet or how life manifests at a planetary scale or what we are as thinking beings. But I think there certainly are a lot of clues to how we might solve those problems. And astrobiology is going to be an incredibly exciting discipline in the coming 50 years with the data that we're getting from other worlds and new techniques we have on Earth. And so with that, I'm going to thank my research group and thank all of you. It's been a lot of fun being here. Great. Thank you.
Thank you so much, Sara, for starting the afternoon on such a profound note. We'd like to take questions from the audience if you have any.
Hi.
Hi, thank you so much for your speech. And I want to come back to a really basic question, which was you're talking about how you can observe the networks in the living planets and how they are more and more complex, right? And then you look at non-living and random networks. And I could understand how on Earth you could probably do that kind of networking, but how do you do it on planets with all of that technology issues and limitations, as you mentioned?
So on exoplanets? Yeah, so that's a great question. So I happen to work with a really excellent exoplanet, I guess he's an atmospheric theorist, I'm not really sure what they call themselves, but he does modeling of exoplanet atmospheres, and he happens to be somebody that's exceptionally good at working with limited data. And so what he actually does is he takes like what's an observational spectrum from an exoplanet. So they take the actual spectral data, and then he tries to infer a distribution of models that might fit that data. So he doesn't assume that there's like a correct model for the atmosphere of an exoplanet. He has some likelihood distribution. And then what we're doing is actually going from that distribution of models to build a distribution of networks. That would be sort of like what's the most likely structure for the chemistry in this atmosphere from this network science perspective. And then what we're trying to actually do with that is see if you could tell the difference between those distributions for systems at different states of being away from equilibrium that might be associated with life. So that's sort of the chain of the logic for that. There's a lot of steps, and it's actually super hard science to really do that in a concrete way. We've been working on it for a couple years, and we're just starting to get to the point where I would almost be convinced it could work. I like intuitively I know it will work, so this is always the kind of thing in science. You have like this idea, but it takes you like 5 or 10 years to really get to like a working, rigorous thing that you can actually like stand behind and say, yes, this will work. And so I think we're well along the path for that, and I'm really excited about it, but it's a really hard question to think about looking for life on exoplanets. And I'm usually the not conservative person in estimating how long that's going to take, or I am the really conservative. I guess this is the one place I am conservative where, I think it's probably going to be like 100 years before we actually can really do serious life detection experiments on exoplanets. But what I'm trying to do is build up the tools to make that happen on a more reasonable time scale, because the uncertainties are so huge. I mean, we don't even actually know how to model these planets. They're really weird. So just to give you another example, like some of the exoplanets that we've discovered, there's just no analog in our solar system. So we have Earth, which is like, one Earth mass planet, and then we have icy giants like Neptune and Uranus, right? And they're much larger than Earth. And we have no planets in between in our solar system, but we're finding all these planets that are called like super Earths in the media, or mini Neptunes, that are probably like just a couple times larger than Earth. And we have no analogs for those in our solar system. We don't even know how to model them. We don't know if they have solid surfaces. We don't know if they have rocky surfaces. So we have a huge set of hurdles to overcome in exoplanet science, which is, the first one is we don't even really understand the composition of these planets, because a lot of the planets in other solar systems are just fundamentally weird and completely different from planets we have in our own solar system. And you can think just in our solar system, we have Venus and Mars, and then we have like icy moons like Titan, which is just this really weird moon of Saturn that has, instead of having oceans, it has liquid methane on its surface, and water is rocks, and it rains gasoline basically, right? So that's just in our own solar system, the diversity of worlds. If you think about other solar systems, it just gets crazier, so we just don't know. And then life could be on those planets. We don't know. So it could just be totally different. Yeah.
Hey Sarah, thanks for the really interesting talk. So my question is about randomness. Is kind of related to what she asked. And essentially I see from what you're trying to do is build these layers of abstraction, kind of like in a machine learning network.
Yeah.
Where you're, I guess you're getting to a sort of correlational point, but your error bars get bigger.
Yeah.
And I think my question is about randomness, and I'm not sure if this makes sense, but when you have a very simple system, when you're describing a simple physics, it's quite easier to say this is random versus this is not random, right? Whereas here, when you're increasing these layers of abstraction, how can you say that what you're seeing actually is random?
Right.
And how do you know? And I guess what I'm...
So, no, I know exactly what you're saying. So I think there's a couple questions embedded here. One is the really profound question of how do you know something's random? And I don't think that is an easy question. And I don't know if I necessarily have the best answer for it, because I don't know if we really have a good answer for that. So when I say random with respect to trying to understand properties of biology, we actually do it in a much more carefully constructed way, which is it's not like a machine learning algorithm where we're going in blind and we're looking for the models to teach us what's going on there. We actually have a lot of intuition about the hypotheses about what physics we think is governing living systems, and then we're trying to ask questions with respect to that physics. And then what we do in my group a lot of the time is actually take a biological system like biochemistry, and we try to build a control for isolating some of the properties. And we do that by randomizing the system in some specific way, so we can understand if we randomize with respect to that property, is biology special or different with respect to another property. And so what we did with the planetary scale biochemistry I showed was we know that life on Earth is organized into things we call individuals, for example, right, like an organism, and then we have ecosystems. So we took the random controls that we had in that case, where we took all the chemistry we know that happens on Earth, and we just randomly sampled reactions to make organisms in ecosystems, but they're not real organisms in ecosystems, they're just randomly sampled chemistry. And they have really different structure, even though when you look at the whole set of those random ones, they have the same chemistry as Earth's chemistry. And what we see is you can actually tell fundamental differences in the structure of those systems. And so that's one way of trying to get at how do you compare biology to non-biology, but do it in a controlled way. I don't know how to really do the life, non-life in a much more rigorous way than that, which gets at this issue of, I really want to understand this is random and this is organized by a different kind of physics. How do I do that? So we're trying to step toward that, but it's a hard question.
Do we have any more questions from the audience? All right, thank you so much, Sara.
Thank you all. Great.
If you have any more questions for Sara, welcome. She's quite happy to take them quite personally at the end of the talk. It's really beautiful to look at complexity in the universe and now zoom back into our planet. And Rika Preiser's talk will offer an opportunity to think about how we're creating futures that meet the deeply intertwined and complex challenges our societies will face in a world that's profoundly shaped by human actions. So Rika is interested in Anthropocene challenges at the Science Society and science-art interfaces, and how artistic practices and interactive modes of engagement could stimulate and advance more positive responses to bring about alternative social-ecological futures. Please join us in welcoming Rika.
Thank you very much, and thank you also very much for the invitation to be here. It's a huge honor. I've also never been to Singapore before, so I'm blown away by just the space, the design, the whole experience of it. Thank you very much for that. I think the link between my talk and that of Sara's is probably, if what driving her research is the question to what is life, I think why I get up in the morning is probably what drives me, is the question of what is the meaning of life. One extra little word. And that's probably just because of my background also. I'm a philosopher, but I'm a philosopher that's driven not by only ideas, but also whether these ideas are actually useful for people living in real worlds, and how those ideas can be applied to solve problems. And that's probably also a little bit based on where I come from in my context, which is Africa. So I've got my little helper here today with me, which is the dragonfly, and the dragonfly will pop up now and then. But just to say that I'm interested very much in this understanding of how do we see ourselves, or how do we find solutions to the future, to think about being interconnected, or this notion of interconnectedness. And this is really for me a kind of a departing moment for thinking about complexity also, is how do we start thinking about the really deep ways in which we are interconnected, not just as humans, but on a planetary scale. How are we humans because of the stones that are in our bones, and how we've been formed, and how can we think about this human nature, interconnectedness, not just as something arbitrary, but something as really important in trying to think about how we will go forward in this world. Okay, so just maybe something really short about my context, because I think it's a little bit more removed from other contexts. So our center, which is called the Center for Complex Systems in Transition, our dean can't really pronounce that word, and I always have to explain to him what it is that we do. We are based in South Africa, in Cape Town, which is the southernmost point, and we're a very small center. I'll speak a little bit about that now, but we're based in Stellenbosch. And we're based, the context in which we work is really the context of Africa, which faces a number of challenges. One of them, maybe if I think about future challenges rather than current challenges, and this is the challenges that are also important to the rest of the world, I think, as it stands today, is if we think about this idea that by 2050, every third child that will be born on the planet Earth will be an African child, we start thinking a little bit differently about Africa and where Africa is going. We have very many images in our head about Africa. If we think about the number of young people entering the region's workforce, we see that by 2050, the number of young people entering the economy or the labor market in the world will be, it will be Africa's workforce. The people that will be entering the workforce will be Africans. At the same time, it's estimated that 70% of the world's poor people will live in Africa by 2030, and 13 of those African countries will be extremely poor. And this sort of extreme poverty will be exasperated with climate change challenges and sort of the way in different ways in which wealth is distributed. But at the same time, if that's the context, there's massive opportunities that will open up in Africa. So thinking about the future of Africa, thinking about, I just saw a program this morning in the hotel on drones that's being developed in Singapore that's going to be exported to Africa, and that what huge market there is for these. So the African market is a huge market if we take these into consideration. And economic dynamism is, and the possibilities to generate new kinds of businesses and to leapfrog into new kinds of governance, and the way in which we think about cities and build cities. These are all sort of prospects that can develop within Africa. So it's seen as a kind of this huge potential space for new things to develop in a different way. So that's the context in which we, in our really little small center that we have, start thinking about complexity and start thinking about what the challenges of the future are and how do we navigate those challenges. Just a few years ago, we started this small center that's really interested in trying to think about interdisciplinary ways of complexity. So in our center, we have biochemists that think about cellular, complexity on a cellular level. We work with people on economists and political ecologists, and I think a huge theme at the moment is this notion of sustainability. How do we think about the food-water nexus in trying to think about how we go forward? So we use this notion of complexity as a kind of a lens or a metaphor to think about the interconnectedness of all these things. A lot of our work tries to engage with these things from a different perspective, and in a sense this notion of complexity opens up a kind of a justification also to do inter and transdisciplinary work and to start looking at what are the different kinds of interconnectedness and connections between different systems, and how can we start thinking things together rather than separately from each other. We've just been through a huge water crisis in Cape Town where they would almost have turned off the taps. But how do we all lived through a kind of a crisis moment of what would it be like to live without water in your household every day. But these things then opened up, and sort of we saw how a water crisis rolls over in a food crisis, rolls over in an electricity crisis, rolls over in a kind of a social meltdown of societal structures and values. So we live through these understandings of how things are interconnected every day, and we try and do that through rigorous science, and we engage with engineers and all the sort of hard science people in our areas. But what we also do is we try and facilitate mutual understanding between these things, between sciences and between practitioners, through dialogues, learning journeys, anticipatory methods, regional capacity building. So we are tasked to actually speak with decision makers about these kinds of things. And the way that we've sort of tried to do that is to experiment with different methods to try and engage these different spaces. And that's, I think, where we've used art processes as a very important pathway to start getting people around the table to speak about interconnectedness and how things are connected, and have different kinds of conversations around the table. We have some wonderful students that we draw from the whole of the continent. And our funding is often sort of development-based. So a lot of the work that we do is funded through the Swedish Development Agency. And we try and also influence conversations about what it is to do development work, sustainability work, understand the notion of resilience from a complexity perspective, and how if we start connecting these things with each other, do our understandings of sustainability or resilience or development work change or not? And that's been a really interesting collaboration over a number of years. We also collaborate with the Sustainability Institute, which is located not far from our offices. It's just outside of Stellenbosch, which is an experimental village where people try to experiment with novel materials, building materials, farming materials, processes. And often people think about sustainability as a kind of a technological thing that needs to be fixed. But what we've also realized is that for communities to be sustainable, we also have to think about social sustainability. So in this village, farm workers live next to professors or accountants, and they start exchanging values and ideas with each other. Often when we stand up and teach about sustainability, people will say, well, that's only ideas for white people. You know, only white people think about sustainability. We, you know, in our community where we don't have running water or food, you know, we don't think, you know, sustainability is a problem, but we want access to jobs, and we also want that nice shiny car next to the pool somehow. So how do we start thinking about sustainability as also in a kind of a social context? And that's what we experiment with a lot in the Sustainability Institute. All of this, is, of course, plays off against this larger backdrop, the more global one, which is the Anthropocene, which is sort of this new geological era that scientists tell us. And through the Anthropocene, I think we start understanding what the nature of the interconnectedness is. Humans are not just sort of living on this backdrop of nature, but we are actually a force of nature, and we're influencing that force in a very real way. I like, usually when I speak to the students, these are quite two fun facts. There's a new kind of an anthropogenic marker, which they call the plastiglomerate. So if the future aliens come and visit our planet, they will see plastic in the stones. And it's been sort of like I say, it's, you know, it's become a geomarker somehow. And then there's also called the Anthropocene chicken, which is another marker which shows that if aliens would come and look at our geological structures and find chicken bones sedimented somewhere, these chicken bones will be much larger than, you know, the normal chicken bones. And this is because of our human influence on how we're breeding chicken and for our consumption these days. So these have become sort of two, you know, weird biomarkers of our planet. And I think what's interesting about this notion of the Anthropocene, it acknowledges that this notion of sort of recursivity, which is a key feature of complex systems, the idea that what happens at certain kinds of scales can't be assumed to just stay on that level or on that scale, but what we're seeing on a planetary level is that these things have influences over many scales. So what happens on local scales from sort of individual communities and individual sort of social decisions plays out on a cumulatively on a global scale and have impacts. We see that, you know, 24% of Earth's surfaces have been sort of converted to cropland. So when we study land use change, we see that what happens in a small village here cannot be isolated or assumed to be not linked to something else, because we have these cumulative effects. And on the other hand, we also see that global events have impacts on local communities or local spaces in a sense. So this notion of the Anthropocene really just amplifies this notion that they are interlinked, things are interlinked in ways that we didn't know before and that we are discovering now, and that these links are real and that they have a real influence and impact on the structure of the Earth and back to how we think about what society is and how we organize society. So we see that the Anthropocene challenge in relation to everything is that Earth and human societies have become really deeply intertwined on a global scale, and that the rate of change and the nature of the change is so much different now than it was before. So we can say it's safe to say that this notion of the Anthropocene can benefit from a deep understanding of the nature of what complex systems are. For me, that is kind of the ultimate expression of complexity in a sense. And just to bring back one of the biggest challenges of understanding complexity, I would say, is this thing that we face is how do we actually navigate complexity? How do we start acting in the face of knowing that things are so connected to one another that doesn't matter what we'll do, we'll probably always be in trouble when we act. So for me, that presents almost the little problem that Dory had when she was facing when he was facing how to try and find Nemo, having to sort of navigate uncharted roads and pathways. We don't really have the tools, I would say the decision-making tools yet, to start making different kinds of decisions about how to go forward in navigating these interlinks and the uncertainty that we are facing with that. So how do we start actually engaging with that? And I think that is a huge challenge, and what we see with the whole discussion around climate crisis and how people want to design for the future, uncertainty is probably, or navigating uncertainty is probably one of the biggest issues that we face. But I'll use this as a small turning point to say that as Marlon and Dory, had to sort of just keep swimming and navigating the depths of the ocean without any clear signposts, they had to start relearning all the other kinds of signposts that they encountered. And I think this is the challenge or the meaning of life for me at the moment, is how do we start learning and putting out new signs for each other to navigate the uncertainty, of which this notion of complexity is probably one of the main challenges that we are facing. And if we start engaging with sort of this understanding of complexity, and you start going deeper and looking at sort of the philosophy of complexity, where my work is focused, I would say that in all sort of the domains that you encounter, you see that this notion of complexity that's linked to deep uncertainty introduces a new kind of a challenge. Like Sara also said, we need new kinds of scientific paradigms to engage with complexity, and we don't really know yet where this will go, or what those paradigms should look like. But there's a kind of a general understanding that there's a shift from old kinds of paradigms, or more standard-based paradigms, to paradigms or worldviews that understand this notion of relationality and how things are interconnected with each other in ways that we don't even know. So, and how do we study emergent properties and patterns that behave, that come up over time. And there's a huge shift from understanding or assuming that the world is orderly and stasis and there's pure knowledge that we can get from well-defined problems, to shifting to understanding that the world is actually rather contingent, it's indeterminate, we're working with systems far from equilibrium and in relational processes, and we don't often know how this will express itself in a kind of a messy organism. So we need new signposts to help us navigate that. So maybe just to, on a very basic level, for me this notion of complexity and how it's expressed in our daily encounterings of that is captured nicely by two colleagues, Jean Bolton and Brian Arthur, who we've recently worked with quite closely, saying that if we need any new science that would be interested in studying complexity would have to be able to look at processes, methods of organization, causal relations, and also seeing these relations as something that is real. So in the old Newtonian worldviews, relations and organizational capacities have never been, I would say, acknowledged as something that is real. They've sort of been cut out, and we've looked at material causes and physical causes, but we haven't looked at relational causes or organizational causes. And that's what the new science of complexity is bringing us, to say, well, patterns come about as real things in the world, and how do we start studying patterns and relations and how these things have sort of causal effects in the world. The work that we are doing is really to try and find, to use these assumptions and to translate that into how do we do science differently. And currently I see that if you look at what's being studied, you see there's sort of two main trends in this field. So the first one is what I'll call computational complexity or computational approaches. And we have Stefan Thurner here in the room, and he's probably one of the leading scientists at the moment, I would say, on how to drive or understand, computational complexity, which really tries to look at the analysis and the quantification of how things behave and come about and what we can say about them on a very sort of deep level where we can compute that. And then on the other hand, they sort of, I would say, is a smaller kind of approach, but it's an approach where we start asking this question of what is the meaning of that? How do we start engaging with that? And how can we, what can we learn from those sort of computational outcomes about what it means to be human and how we make decisions and how we bring solutions to the world? And that's where sort of our work is, I would say, focused quite a lot to see, well, how do we translate those ideas from the sciences of complexity into encountering everyday complexity in our real worlds? I draw inspiration from Donella Meadows, who says that faced by the magnitude of all of this, we are often brought to the edge of our limits and the limit of our sort of scientific understanding, and what analysis can actually do. And to be able to go beyond that, we have to sort of draw on the human spirit. And this is where the notion of what it means to be human comes in for me. How do we start thinking about, who we are in this world in relation to all of this? And if we look at Finding Nemo, we see that there's a specific moment where they get this diving glasses, and there's a little hint in there, there's an address in there, but they're still stuck with this quandary. It's like, how do we start reading human? And for me, this is really the challenge of complexity, is how do we start understanding what is our place as humans in this world, trying to understand the world, and trying to make decisions and plan for the future in this, in a sense. So the huge challenge of learning how to read human again is where we start harnessing everything that we have in our search for knowledge and solutions. What we see from our context is that there's no sort of standard cookie cutter definition of what it means to be human in a complex world, because we know that as humans we can play, hope, dream, create, we can love, we can make choices that harbor paradoxes. So I think that's one of the interesting, usually when I speak to my biochemist colleague, his cells are what I would call reliable agents. They always act in a specific way. But we humans, we can actually be paradoxical. I can be a great scientist, but I can also believe in higher moments of consciousness, or I can engage different paradoxes in one person in a sense. And how do we actually navigate that, bring that into our models of decision making in a sense? For that, we need new ways of knowing and exploring, I would say, how to go forward and how we can sort of harness all of this. And we need new kinds of moral codes. We need new norms actually to enter this space. And one of those sort of norms or values that I would like to sort of introduce is to say we need a kind of a world-disclosing imperative, which is much linked to Sara's work, but on a different level, is how do we start seeing how the world comes about as a real thing in the universe? So how do we start thinking about norms that can break open our understandings of world making and how the world comes about and what it means to be human in these different ways and how we understand the world? How do we start defining norms and values that can actually allow us to understand our situatedness in the world, that can actually allow us to create new worlds and react on the changes that we experience every day? And if we cannot calculate the future, I had a wonderful experience earlier this week in Stockholm where we had a talk with one of the leading futurists. And he was saying that we don't have any data of the future. We don't have any evidence, actually, of the future. Yet, every day we act as if the future is happening. So how do we start, if we cannot calculate what the future is going to look like, how do we make decisions about the future in a way that actually shapes our actions in a real and significant way? And this is where we use, in our context, we've found that by bringing in art processes, art as such, as objects, but also artful processes, and allowing people to engage with art in various settings, is that we can have different kinds of conversations about the future and how we understand what it means to be human in our specific context. This is just a little picture of my students. They do a course on systems or complexity in a kind of an agricultural setting. And I take them to a farm, and we have a wonderful kind of a wine farm just close to where we live and work. And this wine farm uses art. They make sort of art installations around. There's also a hotel, and you can have this experience of walking through art and drinking wine in a very kind of elite setting in Africa. And I take them there to sort of also just experience different ways of how you can produce food. So we go to smallholder farms, and we go to organic farms, and then we go to a big farm like this one, which is like a huge industrial corporation and has a lot of money to bring in arts and stuff. And we're having this conversation about emergence and all these sort of abstract things, and I just wanted them to explore sort of this interface of art and food production in a sense. And we came upon this installation that is outside actually the parking lot. And the students, it's actually a difficult picture. It's the picture of slavery. Because many of these wine farms in South Africa were built on the back of slavery, in a sense, in the colonial times. And this art installation is a kind of a moment where you can stop and think and reflect about that. And if you walk away, you'll see it's this kind of mosaic of little building blocks together. But so if you're close by, you just have the mosaic blocks. But if you walk farther away, you see the image comes into being. It's a picture of a slave. And this writing about that. And the students, they started dancing. They just started hugging each other like that, which I captured there. And they said to me, this is emergence. Little blocks of things coming together to make a big picture. And they could actually experience that. It's something then that wasn't just abstract anymore, but they could actually see and sense it, and they can dance with it. And they actually celebrated their freedom in a way, which was quite spontaneous and nothing that we could ever plan and build into a curriculum to happen. So building on that also, we've used this notion of the what we call an Anthropocene project to create different spaces for dialogue. We have huge funding, people coming to us all the time saying, well, British funding, American, all kinds of development funding, wanting to sort of, engage with climate change and wanting to change the face of Africa and everything. There was one project called Fractal, multi-billion-dollar development project, embedding researchers into 50 cities in Africa to try and get a measurement for what would be a resilient city look like. And there were engineers and mathematicians and anthropologists and managing students and geographers and people measuring air content and stuff like that. And after this 3-year project, we engaged with them because they were doing what they call transdisciplinary work. And after 3 years, we had a kind of a project discussion, and I asked them, so what is the magic thing? What is it that will make cities in Africa resilient? And I thought they would come up with a fancy building structure or technology or something. And they were all unanimous that the one thing that will make cities resilient is dialogue. And I'm like, you're not serious, I'm the philosopher here. You can't tell me dialogue is what's going to make cities resilient. I want a cool, funky technique or technology or material. And they were saying that the biggest challenge is actually to get people to talk together, to understand each other, and to exchange knowledge in a way that they can make different kinds of decisions. So we were sort of drawing on this and say, well, how do people have dialogue in a different way? How can we come together and put our different knowledges on the table for other kinds of conversations to come around? So we see this as our theory of change, is that we cannot maybe have that, we cannot maybe say what it is that needs to be done, or what will bring the change, or what will be the tipping point, or what will be that thing that will allow change to happen. But we can actually create settings for people to have different kinds of conversations, and it's almost built on a kind of a network theory approach to say, well, if you have the same elements in a network, they will always bring forth the same kind of a pattern. But if you allow different elements in a network to link with each other, different kinds of patterns might arise. And this is really how we think about space and dialogue, is to say, well, if we can bring different elements into that space, we can allow people to make different kinds of networks or relations, and different societal patterns or decision-making patterns might come out of that. So it's deeply inspired by a kind of a network understanding. And we're trying to experiment with that in the spaces that we then create. And we've seen that art has a huge way of opening up space and allowing people to have different kinds of conversations. So if you see a conversation as a kind of a node or an edge in a sense, how can we start working with that? So so for the rest of the talk, I'll basically just share some examples of how we've been using art in our processes. It's not very scientific, it's really just experimental, but in all of these art science dialogues, we have usually a huge variety or diversity of artists, scientists, decision makers, societal members, NGO communities coming together to have different kinds of conversations to enable a different pattern to come about. So Anthropocene dialogue is one of those things we did at the Sustainability Institute, engaging a number of different kinds of artists to sort of warm up the space in a sense. We also work a lot with, I would say, bringing art outside of the museum, because in Africa still the museum is a kind of a privileged place, and it's seen that only certain people have access to those kinds of places. So we also sort of, in a way, take art outside on the streets. Here we've installed sort of photos in a community garden. We've installed it on the campus. We've installed it next to Parliament. We've installed it in spaces where different kinds of people live and move. This is the top part is an art installation in the company's garden, which is the first garden that the settlers, the British and the Dutch settlers built when they came to Africa. So it's like our our original space in which, you know, Africa was sort of colonized from. And we've put these artworks in there, and what happened was quite interesting. It was about food and how different food systems come about. But what also happens, and this was unintended, is there's many poor people that live in the garden at night because they don't have any other places to go to. And they were looking at these pictures about nice food and stuff. And the next morning our students would come there and they would want to do interviews with people, and these homeless people would actually hang around there and say, well, you know, what is it that you're doing this, you know, do you have food for us maybe? So we had to collaborate with suddenly we were collaborating with a food production or kind of a kitchen, soup kitchen, and we started using homeless people to become our interviewers. So the guy with the white t-shirt on is actually a homeless person that we sort of just enrolled to say, well, come and be part of this project and start asking questions to your other homeless people. And we sort of just mixed it up totally. Suddenly we created jobs and food and a different space through this art moment. The other one is where we sort of also then infiltrated our museum, our university museum, and we hung our pictures next to the traditional, very stiff and old ways of thinking about art, and we sort of mixed it up and allowed these pictures to speak with the other artworks in there. And then we have sort of designed creative and participatory processes through which we allow people to sit in the spaces with the art, have different kinds of conversations, and engage with it so that it can start influencing the conversations that we have with each other. So using art not as a kind of a mirror to the world, but rather using it to bring things into our field of awareness. And these things that it should bring to our awareness is really this notion of how things are interconnected, and how we shape each other in these relations that we build, in the conversations that we have. One lovely kind of other project is Artifacts of the Anthropocene, where one of our photographers walked on the beach and just collected things that she found on the beach, and they morphed. They crossed the borders between what is alive and non-living, so that this was kind of the feeling of that exhibition. So we have plastic bags intertwined with plastic, lines from sea fishing, but it almost looks beautiful. It almost looks alive. It looks like some sea creature that she found there. So it's also using art to sort of blur the boundaries between what we think is alive and non-living. And then we use one of the bigger projects, and this is where the dragonfly comes in, is a project on water governance and clean rivers. So we have one of the most polluted rivers in our country runs through our university and next to this beautiful farm that people can visit for a number of reasons. It's the highest level of E. coli is found in this river. And there's a huge project to try and see, well, how can we clean this river up and how can we actually start thinking about pollution in rivers. And the only way that one of our students came up with is to say, well, we have to start collaborating and get different stakeholders around this problem, around each other. And they call this the COGO project, which is this notion of collaborative governance. So how do you get industry, huge wine farm industry, to talk to sort of small town inhabitants, university, municipal structures, and in a kind of contested space, because often the problems of sustainability is around contested understandings of, livelihoods in a sense. Big companies want to go forward and make profit. You have people who have livelihoods on the side, then you have the governance structures, and then you have power players. How do you get those people to talk to each other to get the same vision? And they use this notion of the dragonfly actually to open up a space where people can connect on this notion of river pollution. And we engaged our art students at the university, wrote out a competition and say, well, the person that comes up with the best idea wins a prize. And what happened is they chose that design up there to the right. So the graphical layout, which is the wings of the dragonfly, is actually a map, the geographical map of Stellenbosch city. And the blue line that forms the arteries of the wing is actually the river. And the dragonfly becomes the symbol of how does human or social and ecological systems come together to actually form something that is bigger than itself. So people come together around this notion of the dragonfly, and we've seen that it's been kind of a very interesting metaphor. So we have one of the dragonfly specialists in the world, also in Stellenbosch, Professor Michael Samways. And he comes and tells people about the ecological significance of dragonflies. They're like a key bioindicator for clean rivers and clean water. If there's dragonflies around, it means that your rivers are not polluted, and they're like a keystone organism. And then we use that to try and open up a discussion about social ecological connections and how do we govern social ecological or sustainability problems. And we've seen that people have actually ascribed to this notion of the dragonfly the power of change and transformation. They are warriors, prehistoric warriors, and they're messengers of change. And it's sort of influenced how we understand what we call the politics of nature. They've designed games around this, and this is used to sort of take into the boardroom of decision makers. I'll end off with this last example of what we call Seeds of the Good Anthropocene. This is a project that we've run with a number of international partners, where we try to push the limits on this negative understanding that people have of the future and what the future will bring, by thinking about this notion of time. So if we think about the notion of time from a very linear understanding, time is sort of this unfolding of one moment to the next. But if you think of it as a kind of an emergent property, we see that time is something that's influenced from the future, but also from the present, and it has this feeling to it which is emergent, and we call it a thick presence. That means that we have actually pockets of the future that are present in the now, and we call these ideas that shape our future. We call them seeds. So this notion of seeds is actually, we looked at projects that are currently real world projects. They are innovative startup companies, ideas that sort of fill a specific niche in relation to a future problem that we might have. So bamboo bicycles, for example, or recycling or using compost toilets in schools, or transition towns. These are all sort of real-world projects that are responding to some future challenge, but they are now small. They're not mainstream or dominant, but they are doing different things. And our idea is that if we can link these small niche projects together, they can start talking to each other in a network kind of a way, form new patterns, and maybe, you know, in a specific way influence how we think about the world in the future. For that, we've also used lots of dialogues and art, but I think what's more important about this is how this has how this notion of pockets of the future in the present provides hope to people, and how this notion of hope, which is not like the sweet and sugary kind of hope, but it's a kind of a critical, gritty, radical, real-world understanding of hope, starts infecting how we think about things and how we relate to that in a way. And I'll end with a little film that we developed. So we've used this notion of seeds of the good Anthropocene as a kind of a way of thinking about scenarios. So scenarios are also a very well-established methodology to think about the future, and usually you have models that you can extrapolate from, and then you use this extrapolation to do planning. Huge governments use this all the time. But what we're saying is we're using these seeds, these sort of innovative niche projects, and then we do a bottom-up extrapolation of what is happening there to say, well, if we bring these things together and see what's happening in these niche projects, in these seed projects, we can think about radical different futures, because often these scenarios, they just reproduce what's there at the moment, and we need radically different new futures. So I'll play this little graphic harvested video just to give you a sense of how our engagement with, and we've engaged artists in all of these projects as well, to just, you know, help people think radically out of the box, and this is what it came up with.
We live in turbulent times and are surrounded by visions of dark and uncertain futures. Societies are changing, and people are transforming the environment, the entire planet, in unexpected ways. In many places, we are increasingly disconnected from nature and from each other. These are key symptoms of a new geological era, which scientists call the Anthropocene. But there is hope. There are seeds of positive futures all around us, seeds of good Anthropocenes. These seeds are projects, organizations, initiatives that are experimenting with doing things differently and making an impact for the better. Better for people and better for our planet. But for now, these seeds are small, local, and not part of the mainstream. What would happen if these seeds were to grow? If they became towering trees with interlocking networks of roots supporting and nourishing each other? What if these seeds became the way we do things, the way the world works? What would the future look like? This is what we asked a group of scientists, artists, and changemakers at a workshop in Cape Town in November 2016. Starting with 4 sets of very different seed projects and initiatives, we asked the participants to imagine what Southern Africa would be like if these seeds were to grow, combine, and become the new normal. We asked them to stretch their imaginations. We asked them to dig deep. As a result, the participants developed 4 radically alternative positive visions for the future. Although these visions differed in their details, they had many striking commonalities. All 4 futures are deeply shaped by technology. This technology is used in a way that enables people to connect to each other, to develop a shared understanding and empathy, rather than become isolated and distrustful. Technological advances also free people up from working just to pay bills. Instead, people work to contribute to their community, live fulfilling lives, and express themselves as human beings. In all 4 futures, power is highly decentralized, and people actively participate in decision-making. Societies are more equal and fair and value the unique differences between people. Collaboration, rather than competition, is a core ethic. These values extend to humanity's relationship with the environment. Thoughtless exploitation of resources is replaced by responsible stewardship of nature, which is understood to belong to everyone. Most food and other goods are produced locally, minimizing transport and waste. Overconsumption is replaced by flourishing societies in which people respect ecological limits and each other. Idealistic? Yes. Impossibly utopian? No. These are our visions, and the seeds of these futures already exist. Let us nourish them, be inspired to plant more seeds, and let it grow into a beautiful new world.
Great, so you're welcome to also have a look at the website and look at the kinds of seeds and projects that are out there. I could end with wonderful things about what art does, but I want to just conclude with this last statement, and it's a quote by Donna Haraway, and relates to the kind of diversity that we have in the room and the diversity of the talks, which says that by recognizing that we are being in and of the world while shaping the conditions of possibilities for world making, we are called to remember that we require each other in unexpected, real and imaginary collaborations that are realized by being deeply aware that we become with each other or not at all. And that I experienced, that's my foot there, my toe. Recently when I visited Germany, the dragonfly came and sit on my toe, and I realized, you know, we become with each other or we don't become at all, and how do we start engaging with that in different ways? And for that we need everything we have. We need the best science, and we need the best art, and we need the best part of what it means to be human. Thank you very much.
Thank you so much, Rika, for concluding the second part of the program on such a contemplative and a really aspirational note. Would like to open the floor to the audience. If you have a couple of questions, you might just have time for Rika to answer them.
Yeah.
I struggle with this question of like interconnectedness a bit. I work at Grab, and Grab is known as this ride-sharing company. It's like Uber for Southeast Asia.
Okay.
But we're also kind of very interconnected into many parts of society, especially in Indonesia, from transport to food to, you know, healthcare. And we're at a really critical moment right now where, you know, it's either make or break the business, and what's going to determine that is how we treat our people, the people on the ground, right? Even in the company.
Yeah.
One of my main roles is to like connect all those people in the same room,
Yeah.
and to do ideation sessions and have fun.
Great.
And I tell you the truth, we come up with the same thing every time. Okay, so I'm curious about this kind of approach that you have, and it sounds like you've had some good results in coming up with different things when you had. So I'm curious about maybe the how. Maybe that might be something the room might be interested in. Like what did you do in that room at a not at a, you know, have to go into too much detail. We can also pay you to do it too. I don't know, but if you can speak about the mechanics of those.
Thanks.
Yeah.
Yeah, it's $1 million question that you can ask any facilitator. So as scientists, we've had to learn how to become facilitators to start with. So we work with professional facilitators. But I think the bottom line in all of this is when people come into a room, they come into the room with a specific role assigned to them. We have to invite people from the UN and, you know, governments and special important people, and what we've learned is that if they come into the room with a specific role or function, they engage and interact from that function, and it's very few and far between that you will see someone from a local community that doesn't have power or any kind of representation to be able to speak with someone that has power So what we do is we have these creative processes where we break down those kinds of functions in the room so that people enter as humans with their dreams. So in many of these processes, we facilitate, we have techniques where we allow people to first engage with their hopes and their dreams. But even asking people, so what did you dream last night? If you do, tell someone that you don't know what you dreamt last night, which is something quite intimate. But immediately you break down the function. You are not the professor, and you are not the decision maker, and you're not the driver. You're a person. And we connect with our feelings and our hopes, and that allows us to have a different kind of conversation. It's something really small and insignificant, but we've found that it makes a huge difference when you have to start having hard discussions that are quite conflict-ridden. Because people so easily retrieve back into their functions because you don't take responsibility as a person when you make those decisions. Your function makes those decisions. But when you learn that you actually are a real person that have to, you would make different kinds of decisions if you have to draw on your hopes and on your values. So that we don't put out there, we don't really engage with that, but it's this thing about what it means to be human, in the sense that how do we will make different kinds of decisions if we act from an inner understanding of who we are rather than the functions and the roles that are described to us. But then, and there are wonderful futuring tools. So 3 Horizons is one of them. Participatory scenario is one of them. Future wheels. So we can share that maybe afterwards, or I can share some of the yeah. We've got some writing up on those processes. Sorry, it's not a very scientific answer, but it's...
Any more questions from the audience? Thank you so much, Rika.
Thank you very much. Thank you.
We have a couple of programs taking place next month on the back of today's talk, which we would like to share with you. So next week, on the very same level that you are at, we are having a season of programs that look at the impact of climate change on our oceanic environments. And at the center of the program is an exhibition called Climate SOS Changing Course 2019. So it explores humanity's relationship with our planet. It outlines the challenges in our current global patterns of consumption and production. And it provokes answers to this one central question of how can we change the course of humanity. We have another 2 talks that's taking place in October. Gunalan Nadarajan is joining us to give a talk that will make a passionate argument about why cross-disciplinary focus in tertiary education is really important. And at the end of the month, we close off with a talk by our French artists, Adrian M. and Claire B., who will be sharing with us performances and exhibitions that playfully blend reality and virtuality, and they will be talking about their interdisciplinary projects. Thank you so much for joining us this afternoon. It's been so lovely having you in the space. And please join me in thanking our speakers for today, Sara Walker and Rika Preiser, for their amazing talks.